Hello, I have explained the fitted value approach in a general setup, and compared with the first approach, the IV approach, the fitted value approach is more intuitive in the sense that it shows how the effect is transmitted from Z, the instrument, to X2, and then from X2 to Y. So, for example, we can study the rank condition in the fitted value approach in a more intuitive way. So I prepared a simple 2x2 case. So I consider y is determined by x1 and x2, and both x1 and x2 are endogenous. In this case, there is no exogenous variable. So both are endogenous. Excuse me. So there are separate equations for x1 and x2. So there are two endogenous variables, y equals to x1 and x2, and x1 is determined by z1 and z2. x2 is also determined by z1 and z2. And they have their own coefficients. So it's a triangular equation system. And in this case, the idea is the same. We are going to replace x1 with this guy. And we are going to replace x2 with this guy. So point is, we are going to drop, what we want to do here is we will drop xi1 and xi2. Then from this, we can study what we can do and when we can identify and when we cannot identify both beta 1 and beta 2 in this simple model. When you have two endogenous variables. When you have only one endogenous variable, the solution is simple. Whenever gamma is, so whenever the relationship between x and endogenous variable and the instrument is if their correlation is non-zero, if they are correlated, then always you can identify the coefficient. But in this case, when you have two endogenous variables, then you have to think about the relationship between x1 and x2 at the same time, not only between x1 and z1 or x1 and z2, but you need to think about their relative relationship. So, for example, let's think about one by one. So, suppose that the first case where beta 1 is not identified is when gamma 1 and gamma 2 are 0. That means when gamma 1 is 0, gamma 2 is 0, you have 0 here. So remember, this part is the only variation in x1 that can help identification. So this part is the only part that provides information to you. So the other part, the remainder, is useless because it is correlated with epsilon. So the variation in psi does not help at all in identification. So therefore, if gamma 1 and gamma 2 are 0, then you have no informative variation in x1. So beta 1 is obviously not identified. So beta 2 can be identified. Beta 2 can be identified by the IV approach, but fitted value approach fails because the second stage regression does not work because x1 is gone. x1 will be 0. x1 hat will be always 0. So the two-stage approach doesn't work. But it is an interesting example to see what happens when. So this is the case. You may interpret this case as the case where one endogenous variable has no correlation with any of the instrument. So that's the first case. The second example, gamma 1 is 0, beta 1 is 0. So now this is 0, this is 0. In this case, the problem here is Z1 does nothing. So z1 does nothing in both equations, so z1 is useless. It does not do anything. You just simply, you may erase this part. You can simply erase this and this. Then in this equation, in the system of equations, z1 has no role at all. It does not do anything. So obviously, beta 1 and beta 2 are not identified. Or you may think, if you think about the second stage regression model, second stage regression, x1 hat is a function of z2, x2 hat is another function of z2, but in the end, they are multilinear. So both are simply depend on only one variable. So one variable cannot generate two variables. That's the problem. So, or you may think that one instrument cannot identify two endogenous variables. So you may see this as a multicollinearity problem in the two-stage approach, in the fitted value approach. And the basic fundamental problem is that Z1, one of the instrument, has no correlation with any of the endogenous variables, or the number of instruments is smaller than what you need. Third equation, third example, third case is when gamma 1 is 0 and delta 2 is 0. In this case, there is no problem at all. Your identification works well, because if gamma 1 is 0, that means x1 depends only on z2 and delta 2 is 0, so that means x2 depends only on z1. So one instrument takes care of one endogenous variable respectively. So one instrument, one endogenous variable, kind of one-on-one, one-to-one mapping, one-to-one defense. So everything is nice. There is no problem, no multicollinearity. As long as Z1 and Z2 are not multicollinear, your identification does not have any problem. So this is the case. Another interesting example. Think about what's the difference. And case number 4, multicollinearity between Z1 and Z2. Then obviously beta 1, beta 2 are not identified. Z1 and Z2 are multicollinear. That means even if you have two variables, but basically you have only one. You have only information as much as only one variable. So same problem. One instrument, in the end, effectively one instrument for two endogenous variable cannot identify. So multicollinearity problem also goes back to this case, example 2. And the final example, if the ratio is the same, if those ratios are the same, then the problem here is when you think about x1 and x2, x1 hat and x2 hat, so this part and this part are proportional. So gamma 1 and delta 1 are proportional to beta 2 and delta 2. So then x1 hat and x2 hat will be perfectly proportional. So another multicollinearity. So that is another problem that causes a multicollinearity in the second stage. So that is anyhow, as you can see, among these 5, whenever there is no identification problem, whenever the parameters are not identified, it is a kind of multicollinearity problem, because in our approach, in our fitted value approach itself, the purpose of the fitted value approach is to decompose the endogeneity problem, to fix the endogeneity problem with two classical linear regression problems. And in the classical linear regression problems, as long as there is no endogeneity, then the other problem is the multicollinearity. So if you have multicollinearity somewhere inside within the two-stage regressions, one of the two regressions, then you are going to see these kind of problems. So think about these and connect I want you to connect the concepts between multicollinearity and endogeneity and fitted value and like a number of endogenous variables together. So you should be able to switch between them freely. And some general discussions. So the exogenous variables x1 will be automatically included in the instrument. So in the first stage regression, z2 is an additional variable from outside. X1 is also included because it is not correlated with epsilon. So because this guy is not correlated with epsilon, there is no problem in including x1 here. So then it is always better to include x1 in here to have a better estimator, better efficiency. You can have more variation that you need, right? So exogenous variables will be always in instruments, and endogenous variables may share the same instrument. So the point here is, as long as some variable is uncorrelated with the error term, then you have to put that everywhere possible to explain the endogenous variable, because additional instrument will capture a little more variation. Even if 0, there is nothing you lose. So having more variation will help you. And the relevance condition is clear in one-dimensional case. In one-dimensional case, relevance is simply covariance, non-zero covariance. But when you have multiple variables, you have to have a little more complicated concept, which is the rank condition. So rank condition is, I skipped it. Rank condition is stated this way. So the rank between x and z prime, xz prime expectation should be k. Or you can think it as a kind of covariance matrix. So the rank of the covariance matrix is k. That is, this is the extension of the relevance condition, non-zero covariance condition. So this is also about, as I said, this expectation is a covariance. So it is also about the covariance, non-zero covariance assumption. And for the IV approach or the moment approach is more general because it does not require this, right? It does not require this, or it does not require additional linear regression. So, but fitted value approach is more popular because it's easier to understand and easier to implement, because you can just use linear regression, the classical linear regression methods repeatedly. So fitted value approach is also very popular in applied work, but the moment approach, IV approach, is theoretically more general. Okay, I'm going to stop here. See you in the next video.